I want to get into this episode what exactly is magnetism, and if we sort of go back, there's sort of two views. There's magnetism is, we've got the simplistic consumer view of magnetism. Magnetism is what magnets do, and another view is magnetism is an aspect of nature which leads us to other things, and we're going to get that second view. To start off with, magnetism was not seen as a property. It was seen as really basically what magnets do. They picked up these early magnets and they noted it did it, and they didn't think of it as a property. They thought of it as a power of the object, not a power that the object possessed. And that power could be in other things, sort of fairly complicated across. Now, that has actually not gone very much, that ancient view has not gone very much more sophisticated into our schools, because we have a kid and we say, we're going to teach you about magnets. Here is a magnet, and pick that up, feel that, magnet, not magnet. And then it does these sorts of things, and there are these properties which I can tell you about, which are very important because they're going to be in the test. I'm going to tell you that opposite poles attract, north and south attract. There's poles, and there's something to do with the earth, and magnets are very useful things, and it doesn't get very much deeper than that. And so that's sort of the ancient view of magnetism, and it took a while before people actually said it's not just an object. A magnet is not an object called a magnet, and it's magnetic. There's actually a property of magnetism in that object. And then that got a bit more sophisticated with Gilbert and Dr. Gilbert and the Elizabethans in the Renaissance began to actually prize. No, it's hard to understand. It's sort of like if you only ever had Cocoa Pops all your life for breakfast, you wouldn't be able to associate different styles of cereal or being full from eating cereal as from Cocoa Pops. It's a bit hard to go, but our schooling has not gone much more sophisticated than that. However, science had to be a bit more sophisticated, and we began to get these properties in terms of, once I used magnetism to generate electric motors or electric fields, we began to write equations, and those equations eventually began to help us as a window into the rest of our universe. So magnetism, very much as I want to present it to you, is a window into the rest of the universe. Now, the simplistic idea is from that rock. You know, a rock is magnetic, so it's got to be made of things. It's got to be a negative, a north and south pole. And we've indeed, when we've actually gone down that and asked that question over and over again, is it a physical thing? Is there something, a north pole and the south pole, and are they separate? Is there some way of it going? And people, this is a very ancient view, and this is really inside the view that we teach at schools. Very wrong. There's sort of a little level up from that, and that is a real thing. Magnetic field lines. Magnet has field lines, and they're real. And it took a lot of effort in terms of magnetic field lines, and the view that we teach in school was basically a hallucination, a daydream by Faraday. He sort of imagined field lines as hairs, physical hairs, and he begged and pleaded with this leading mathematician James Clerk Maxwell, to see if you can find out that what's the mathematics for it. And incredibly high level mathematics, in my view, came out just about 10 years after the use of magnets. So magnets had a use to stick to things, but now to make things electric fields, the combination with electric fields came across, and we started to have Maxwell's equations, and we have our second definition of a magnet. So a magnet is what happens, magnetic field is what happens when a charge moves, and that's essentially what magnetism is. Magnetism is a charge, the force from a charge moving. It so happens that when you go down the special relativity path, that the electric field, as you approach the speed of light, in your frame of reference, someone's magnetic fields turn to electric fields, and their electric fields turn to your magnetic fields. it's this coupled to link together, and electromagnetic radiation is very much in the speed of light. Now we're going to get in that straight away, but you can well imagine that if you do understand special relativity and you do understand Maxwell's equations, and I have not a complete understanding, but I do understand the actual steps of it, you're going to have difficulty with someone who says, "Oh look, it's north monopoles and south monopoles, and that's the way to go." You say, "Oh no, there's this other view where a charge, we can really understand a charge creates an electric field, a charge and electric field, we put them together. What you need is a charge motion, and you need another thing called space." So it is a property, the Maxwell's equations have coefficients in them and relationships in them, and they apply to our space. So very much magnetism is a property of our space. A magnetic field travels through a space. It couldn't travel through a void. It has to actually travel through our physical space, and that's an important thing to know. So we're going to go into what is a magnet. A magnetic field is caused by a moving charge. A static magnetic field line is caused by a charge moving in a circle. And there are three ways that things move in a circle. Now the assumption is that my reality I teach at school is good enough for everyone, and unfortunately I have to tell you that's not true. This is going to say reality isn't true. No, your reality is only a fraction of the truth. Now the first way I can generate a magnetic field line or field is that I can get a charge and I can move it in a circle, and Maxwell's equation says that that current across there is the amount of magnetic field line fluxing through there. So that would be curl nebula, curl B. The curl of B, it's called, is the current, the circumventing current from it. There's no magnetic charges, so B can't erupt from you can't have a positive a north pole with lines going across it and into it. You just that cannot be. There's thousands of reasons. So Maxwell's equation says that's not true, and he's saying, well, for our space, for our universe, there's no such thing as that. But there is this property of a circular charge, and I can actually make a charge go in a circle in a solenoid or a motor by putting it in a wire and getting the wire to do a loop-the-loop, and it goes in a circle, and that will generate a magnetic field. So essentially that's an electromagnet, and as I promised you that there's there's three versions of it. That version is 100%. That is what a magnetic field is. B is the flux of B, or the amount going through a surface is proportional to the current. And that's what B is, unfortunately. No more, no less. It's called Amperes Law, an Ampere view. There's the Amperes view, and then there's a school view of north monopoles and south monopoles. That's out, and Amperes Law is in. However, we have these problems that Amperes Law also says that if you go like that, if I have a coil, it will radiate energy, and this is true. This is one of the problems of it. So that's version number one. Fortunately, if I have a mobile phone, I don't have a mobile phone here, but mobile phone here, I do have your little device has charge, and it rotates around and radiates out this as well. The rest of the world operates like that. But obviously electrons, when you get down, so this is the first one, the middle line, electrons when you get down are not radiating. If I hold the mobile phone, disconnect the power, it's still not putting out energy, yet the electrons must be going around. It can have a static magnetic field in them, and that is called the orbital angular momentum of electrons. Now that generates a magnetic field, and that is, if I have an electron in an atom, and it's going around, somehow it appears, in terms of generating a magnetic field, I can measure the electric field from an atom with an electron in it, and that B is telling me that the current is going around in a circle. So from that magnetic field I can measure that B, and therefore I know that electron is going in a circle around here. But that electron is going in a circle and it's not radiating. I think this is Bohr says they go in circular paths but they don't radiate. How can that possibly be? Well, 1923 they began to work out how that could possibly be, because motion can be two things. In quantum mechanics, you can get a object. I'm going to grab something here, an object, right, and it can move. Or there's another way things can move in quantum mechanics. Or would you say move? I don't know. It's something which is so small it doesn't have parts, so therefore you can't say I can't say have an ant on this which moves, or a mosquito in this case, an ant on this which moves across, because this is the smallest thing possible. So how can you have the smallest thing possible which has movement? And this is where you have quantum mechanical movement, and that is the complex derivative of the wave function. There you go. It's strange. It's d wave function dx. The complex derivative is defined as equivalent to the momentum. It's the property of a stationary wave function, which looks the same to me and you, but if I look at the phase of it and look at the complex of it, I can see that it's actually got the property of motion, because when I take that property and put it in the momentum equation, it gives me the energy of it. So it's not moving in the way that we sense, but it is moving quantum mechanically. And so electrons themselves rotate quantum mechanically, and how they do it is that they have a complex phase sweeping through it, proportional to the energy, e to the it, e to the iet, something along those lines. That they're more energetic the more it goes across. So what you do is that your S-shaped orbitals, your spherical orbitals, are moving, but they're moving inwards all the time and they're not projecting a magnetic field. Whereas a P-shaped electron is got its phase, and its phase is say if you've got your dumbbell P-shaped electron, the phase is going through it up and down. And so your complex phase is the way something stationarily moves. Now to us, we can't see the complex phase. If I had a big electron, it would, and expanded up, it would look, I suppose, fuzzy and big. Remember, electrons don't have surfaces. Quantum mechanical wave functions are not like this. This has got a surface. An electron doesn't have an inside or an outside, because it doesn't have a surface, a boundary layer. You have a threshold layer, but it's not a surface. It's sort of like landing your aircraft on a cloud. It will just go through it. So electrons don't have surfaces, and so how does something which is so small that you can't put a pointer, you can't spin an electron, well, yeah, but this is unfortunately, I'm going to tell you, you can't spin or rotate an electron because it's too small. It doesn't have a part on it to spin. I can spin this, but that is because I can see that part and that part. You can't actually spin an electron. You can spin, I'll just go across it. So this gives you your magnetic field from a solenoid is mu naught, number of turns times the current divided by the length is your solenoid. Then for an atom, it's the charge on the electron, fundamental charge on the electron, the angular momentum divided by the mass. I don't know whether you need a mu naught in there. You probably didn't need a mu naught in there. Same thing, you mustn't need a mu naught in there. And it's got a gyroscopic ratio, gyromagnetic ratio, I think it is called a G factor of 1. That is, it is exactly, it's in our space. We can't see it, but it's rotating. So this is a bit of a brain teaser for it. That is, from kiddies, you're told by, which I can imagine, particularly angry teachers, this is a magnet. Then if they ask more questions, why do you want to ask that? Then they might give a bit of explanation that you can have a non-electromagnet with atoms, and the atoms have spinning electrons, and they actually physically spin, but they don't. It's start of quantum mechanics, and essentially you really have to tell the kiddies this. And as I said, there was going to be three points to it. You've got your solenoid, you've got the atom, and the atom having our frame rotation due to the complex phase going around it. And then you can actually have the electron by itself. And the electron by itself has a spinning, but not in this universe. So that is the spin. So you've got the electromagnet macroscopic movement. You've got the internal atom movement, the L angular momentum. There's another type of angular momentum called spin angular momentum. It is, for some reason, they think the first view of it is an electron is actually physically spinning, but an electron, of course, can't physically spin because it's too small. It can't have a spot on it. Actually spins in a dimension, a hidden dimension that we can't see. You can imagine this, you're trying to tell, this is why we're having a master class, because you can't obviously say kiddies, and you can imagine them being a bit bored, and they'll wake up and you say, oh, it's none of it's real. But you have an electron and it actually can't actually physically spin. So it's an object. Let me get another twig or something like this, and electrons physically don't spin. So they have an angular momentum, and essentially when they go right down, and they lose properties all the time as you get smaller and smaller, they lose the property of having a surface, they lose the property of they have the mass as a fundamental property. It is fundamental. So what it means is fundamental can be, when we say something has a fundamental property, we mean that fundamentally it has no explanation in classical physics. It's no explanation that you can understand. It has the fundamental property of charge. It has a fundamental property of mass, although I could calculate it across there. And it has a fundamental property of angular momentum. That is, angular momentum is your Torville and Dean. That gives my age away. Your figure skater going around in circles, spinning around, and it has the fundamental property of angular momentum. And indeed, if you can get things to rock with the angular momentum. Now, this angular momentum is the electron. Physically, it has the property of spinning, but not in our dimensions. It's really fascinating to actually go across it. And so this spin is slightly different. So it physically does not have any, the electron itself doesn't have another phase. An electron can sit there with one phase, yet it will still have a magnetic field, and it will be as if it is spinning. That is, the electron will have, it will be either far away going slowly, or it will go in a smaller amount. It will still have the same magnetic field coming out. And so the actual magnetic moment, now let's talk about what magnetic moment is in a second. The magnetic moment of it will be G, the gyromagnetic ratio, the charge on the electron times the spin momentum, S, divided by the mass of the electron. The mass of the electron is pretty low, so the mass of the electron is very low. The momentum of angular momentum is the speed times the radius. So it's kilometers per second kilometers. This is so if it's further out and it's still going quickly, it will give your total orbital angular momentum. And so this, you have the m there to give your just the velocity, your velocity of your charge. So if you just have that and divide it by the mass, you'll get the velocity of the charge. The spin divided by the mass will give you the velocity of the charge times your gyromagnetic ratio. Now the gyromagnetic ratio. I know I've never actually said it before, and that is in fact 2 and a bit. What? Yes, my universe is big where I can imagine it. Tough for schools, and really tough for schools. And this is the spin, gyroscopic. Why is it 2? Well, there's something which means that when it does a spin, the electron's actually going twice as fast. So the electrons actually has to travel twice as fast to make an angular momentum journey. That is, that you get a factor of 2 magnetic field, which is a bit of a bastard some of the time. A factor of 2 and a bit for every rotation, hidden dimension rotation. So it is rotating, but for when it does a rotation, it's travelling twice as far. There's a factor of 2 in it. How does that come? Now that comes out of the maths in one aspect, but the physical interpretation is that the electron, when you rotate the electron 360 degrees, internally it's actually going 720 degrees. That is, the electron has SU2 symmetry, spin and a half, and therefore it travels 720 degrees around to get back to the same point. So your angular momentum gives twice the current, because it's actually traveling twice the angular amount. And this is physically fixed, that when they measure the strength of a magnetic field due to an angular momentum, you get this factor of 2. Then you also get another thing called a vertex anomalous gyromagnetic ratio, which is sort of, I think, a thousandth, a tiny smidgen more. And what is happening is that the electron, you have Fermi diagrams. It's called a vertex function. I can draw it, but essentially the electron spends part of the time in a froth, quantum mechanical froth. This is true. Quantum mechanical, it is true because we can measure it. It's there. It goes across, and now I'll give a bit of a shock at the end of it. So you've got this thing, and the electron momentarily breaks apart into becomes an antiparticle, becomes its antiparticle, just ever so slightly, in the smallest fraction of time. And when it's in that time, it's got a massive charge. So massive charge in that tiny fraction of time. That's called a vertex correction, anomalous correction, and it's sort of hard to imagine. Well, it's obviously almost impossible. Well, it is technically impossible to imagine higher dimensions. It's you know, at the end of the day, the deal that for all education, I can give you a block and go. You unfortunately can't do it, and this is why you're probably having master classes. So your spin on your your spin magnetic field is actually higher. Now it's also got another thing, is that because it's a symmetry field, it can either point with the field line or against the field line. It has no option to point any other angle to the field line. Or it's it is fixed. It can't vary. It can't move across it because it's actually physically quantized. So there's all these properties from it coming up here. So let's just do this in review. So at school and in the ancients, you were taught everything is physical, and if I can pick it up, I can it's a big thing to imagine something smaller, but it can only get smaller. It doesn't change physically. I don't have to suddenly at a point in time, okay, switch on advanced maths, and eventually you do have to switch on complex numbers to get into your physical electromagnet, to the atomic electromagnet, to the actual electron. So you eventually go complex maths, and then at this point in time you go supersymmetry, or SU2. So the XYZ is SU3, the quark and all that sort of standard models SU6. Unfortunately, this is why you're doing this magnetic field class, and we get this amazing factor of 2. So the spin contribution has got this factor of 2 in the magnetic field aspect of it. 2 and a little bit, and 2 and a little bit easily measured. Well, it is pretty easily measured, and the physicists have measured that, and then they turn around and go to the classroom, and the classroom is still teaching the ancient stuff, and you go, I can't really tell you my result of my equation. But the important thing is that where's S2? Where's the third way, the actual high SU2 intrinsic magnetic field of an electron? An electron by itself is a magnetic field. It has got a magnetic field with it, and that is the field in fridge magnets. In fact, there is actually very little contribution of magnetic field ever from your orbital. It has a big effect in terms of lines, magnetic lines, but in terms of practical stuff, you've got your electromagnet and your SU2 symmetry, your fridge magnet there. Now, we have a problem in terms of that's the story, that is how it's actually told. How do you actually explain all of this? I don't know. But Masterclass is one, and some of the experiments coming up will help explain it a little bit more clearly. That's true. Look it up. What I'm saying is absolutely true.